talk about the basic concept of calculus with parametric curves. So first of all, we learn rectangular coordinates. So for rectangular coordinate, you use that in integral calculus and differential calculus a lot. So for rectangular coordinates, so let's say we have a parabola. So the parabola, at the vertex we have a horizontal tangent line, so that means the first derivative is equals to 0. When x is less than 0, we have a tangent line that is going downhill, so that means at that point f prime of x is less than 0, and then when x is greater than 0, we have another tangent line, so the tangent line is increasing, going uphill. At that point, f prime is greater than 0. Alright, what about the parametric curve? So for the parametric curve, we have one parameter t that links two functions. One is function x, the other one is function y. So for the parametric curve, so I have a example of parametric curve for you. So we have a yellow curve, and then we have a particle. The particle follows the path of that curve, right? So let's say I have a specific location. Do you see there is a big yellow dot? So at that point, we have a x comma y. So what is x comma y? X comma y is a location, right? So x comma y, when x comma y is a location of the curve, but the x comma y does not have the time. So behind the x there is a t, behind the y there is a t. So other than just x comma y, the location, so we have to dive one step deeper. So there is something behind the x, there is something behind the y. I can use t to explain x, and I can use t to explain y. All right. Okay, so let's say we have a parametric curve. So I'm going to just give you an example. So this one is just an parametric equation without any number. So x is equals to some t, y is equals to some t. What I am trying to do is I am trying to convert this to a rectangular equation. So what I am going to do now is, for the x function, I am going to write t in terms of some x, and then I will plug in this t equals to some x to here. So now what do you get? What is the result going to be? The result is y equals to a function of x, right? So y is a function of x. So now that means y equals to some x. So now we just return to differential calculus and integral calculus, right? So we have y equals to some x, and then let's say you want to find the slope of this function y. What do? You find y prime, right? So y is a function of x. That means the derivative, using the derivative notation, that is the derivative of y with respect to x. And then, but no, look, how do I get the y equals to a function of x? We got that from a parametric. So in a parametric equation, x can be equals to some t. That means I can use the parameter t to describe the behavior of x. So in here, I have to make a note that x is a function of t. All right, so we put a little stop right there. So the next thing that I'm going to do is I am going to give you an example of parametric equations. So let's draw a line to divide the works, and then allow me to switch to another color. So here is what happened. I have an y-axis and I have an x-axis. So that is x, and then that is a y, and then this is my starting point. So I have a particle, and what I'm trying to do is I want to shoot this particle up. So the path looks like a parabola. So I'm trying to shoot this parabola and shoot the particle to that direction. So can you give me the parametric equation? I'm going to give you that right now. So here is the parametric equation. The x function is equals to 24 square root of 2t, and then the y function is equals to negative 16 t squared plus 24 times square root of 2t. All right, so this is a parametric equation. Now I want to convert the parametric to rectangular. What do I do? So here is the first step. So the first step is I would like to isolate the root 2t on one side. So x divided by 24 is equals to square root of 2 times t. So that means I divide both sides by 24. Also, I need one more pieces. Other than that, I also need to divide. So this one, we need to keep this. This one, we need to keep this. Other than that, I need to prepare one more ingredient, which is also divide both sides by square root of 2. So 24 times square root of 2 equals to t. And then you square the both sides for me. So this we have x squared 24 times 24 times 2 is equals to 1152. So now we just prepare all the ingredient for the conversion. So let's rewrite this y. So y is equals to negative 16. T squared, I just got it. So that is x squared divided by 1152. And then you square that because that is a t squared. Oh, actually you don't need to. This t is already square. And then you add 24. So now, do you see that the 24 root 2t, I just got that right here. So 24 times x divided by 24. We don't need to simplify this at all. So this one is y in terms of x, right? So y is a function of x, but don't forget this came from a parametric equation. So in a parametric equation, we have to specify that there is a t behind the x, right? There is a t behind the y. Also, there is a t behind the x. So the x comma y is only a location. So behind the x and the y coordinate, there is a t. The t is the parameter time that describes x and describes y, right? I have to specify, but x is equals to 24 times root 2t. So don't forget that x can be described, can be explained using t. All right. So now, so the f of x, right? So the y equals to some x. So that means we have y equals to f of x. So y is equals to f of x. Don't forget that x is equals to some t, right? So this one we can rewrite that as x of some t. Okay. So now the f y equals to f of x, the x, the independent variable x, this x right here is equals to some t. So that means that is equals to, we are going to replace the x with x of t. Okay, now, so we have y equals to that. Okay, now, I want to find the slope. How do I do it? If you want to find the slope, then you have to differentiate, right? So when you study differential calculus derivative, when you find the slope of a curve, you have to take the first derivative. Let's do the first derivative right now. So the first derivative is y prime. So and then on the right hand side of y prime, do you see there is a composition function? We have a function x inside a function f. That means we have to apply a chain rule, right? So first, we take the derivative of f prime, and then x of t, and then using the chain rule, we also need to take the function of the inner piece, right? So that means we have to multiply x prime of t. So let's say, in case you don't remember, so allow me to switch color. I'm going to give you a quick example. Example came from differential calculus. So this is an example came from differential calculus. So let's say y equals to sine of x to the fifth. I want to use chain rule, so y prime, the derivative of sine is cosine. And then you still write the x to the fifth, right? So using chain rule, you also need to take care of the derivative of x to the fifth, so which is 5x to the fourth. Just this is why we have x prime of t. So you have to take the derivative of the outer piece and then you multiply the derivative of the inner piece. The inner piece means the inner function, because the y equals to sine x to the fifth. Sine of x to the fifth is a composition function. Okay, so let's go back to this problem. So I'm going to write a sentence. So y is a function of x, and then x is a function of t, right? So that means the dy dt, so take the derivative of y with respect to t. So that this one that gives you the derivative of y with respect to x, which is the f prime of x in here. So this is here. And using chain rule, you also need to take the derivative of x of t. So that will be a dx with respect to dt. So this one is this piece. All right. So, and then I have to solve for dy dx. So solve for dy dx. Where is dy dx? dy dx is here, right? So solve for dy dx. That means you have to divide both sides by dx dt. So solving dy dx. So finally, so we have dy dx equals to the left hand side divided by the dx dt, right? So we have a dy dt divided by dx dt. Okay. And then that has a name. So this is the parametric curve of derivatives. So this one is called the parametric curve of derivative. So what is that equal to? So when you do this, we are looking for the slope. So we are trying to find the slope. We are trying to find the slope of the tangent line. Derivative, right? Derivative means slope of a tangent line of the tangent line to a parametric curve. So there is a t behind the x and y. That's why we want to do this without eliminate the t. Okay, again, let's draw a curve. So let's say this is my parametric curve. And then I have a point right here. So the location is x comma y. And then the x can be described as some t. The y can be described as some t, right? So what we are trying to do is this point has a slope, right? So this point has a slope. The dy dx gives you the slope of this parametric curve at this point. So the dy dx is equal to the slope at any point. And then how do you find the exact value? So to find the exact value, you have to give me t. So you have to give me given a t. So I am going to use t to calculate the exact location of this point, and then I can find the slope. I can that and then find the slope. So what is this called? This has a name. So this is called parametric form of the derivative. So for the parametric form of derivative, I'm going to put that right here. So parametric form of derivative. So we have a smooth curve C. We stand for big C, so that is the curve right there. So we have a parametric equation. X is equals to f of t. Y is equals to some t, right? We call that a g of t, just two different functions. And then the slope of C at a specific point, at any point, is equals to dy dx equals to dy divided by dt over dx divided by dt. Since there is a denominator, you have to specify that the dx dt can never be equal to 0, because 0 cannot be a divisor. So this is finding the slope. So in back in differential calculus, do you still remember what the second derivative represent? The first derivative represent the slope, so the second derivative represent concavity, right? So for this definition, what is for this parametric form of derivative, what about other than the slope, what about the concavity? So for the concavity, I will just give you the formula. So that is the second derivative of y with respect to x that is equals to d dt times dy dx divided by dx dt. What is concavity? So concavity, so let's say we have a function, the curve looks like that, one piece and then another piece, and then this one is concave up, this piece is concave down, and this point is the location where x and y changes. So this point we call that an inflection point. What happened when the function is concave up? When the function is concave up, that means within that interval, the second prime is greater than 0. So let's say we have a concave up, so that means this point is a local minimum, right? How do you use the second derivative test to prove that this is the minimum? First, at a minimum, we have a horizontal tangent. Horizontal tangent means the first derivative is equals to 0. Other than that, you also need to show that the second derivative is greater than 0. So at a horizontal tangent, we have a mean or a max, but if the function is concave up, use a parabola facing up, then at that horizontal tangent, we have a minimum. What about this point? This point is a maximum, right? So it's a maximum. At that point, the first derivative must be equal to 0, and the second derivative must be less than 0. So concave down, and then at a horizontal tangent, that point must be a maximum. All right, so let's do the slope one more time. So for the slope, let's use this color. So for the slope, we have a parabola. So this point, and this point, this vertex, we have a horizontal tangent. So f prime is equals to 0. And then at this point, the tangent line is going uphill. So f prime is greater than 0. At this point, the tangent line is going downhill. So f prime is less than 0. So every time you find the slope, so find the slope at this point. So let's say the slope at this point, there is a value, right? And then you can use that value, which is the slope, to build a tangent line, the equation of a tangent line. So of course, to build a straight line, what ingredients do you need to build a straight line? You need a slope and you need a point. That point is x1, y1, a point on the curve. And then what is the equation of the tangent line? So the equation of the tangent line, we are going to use the point slope form, which is y minus y1 equals to the slope times x minus x1. We will be using that in the examples. So that will be all for the introduction. Let me know what you think in the description, in the comment section below. If you think my instruction is helpful, please like, subscribe, and share the video out for me. I appreciate your help really much. That will be all in this video. Signing out for now. I see you all in the next one.